Hi everyone. In this video, we want to learn more about working with Taylor series. In particular, we'll learn how one Taylor series can be used to create another, and we'll practice doing this by modifying Taylor series via substitution, integration, differentiation, and more. So there are really four primary ways we're going to talk about transforming Taylor series, and we'll look at an example of each of these in turn. So the first way is by substitution, by simply substituting in sort of a change of variable, although it has to be of a specific type, into a Taylor series that's already known. The second way is by integrating or differentiating a given Taylor series. The third way will be multiplying a Taylor series by a power of x. And then the last way will be by reindexing. We'll conclude the video by looking at one example that uses a number of these techniques to determine the value to which a given series converges. So let's start with substitution. So imagine that you were asked to find a Taylor series for the function f of x is equal to 1 divided by 1 plus 2x squared, centered at x is equal to 0, and to find its interval of convergence. So the first piece here, you want to find a Taylor series for this function. Now, the standard way to do this would be to sort of write out the derivatives, the function value and its derivatives of various orders at 0, and try to find a pattern. Certainly you could do that, but here we can actually take advantage of something else, namely that if I look at this function, I can realize it as a composition of the function 1 over 1 minus x and the function minus 2x squared. Okay. Now recall that I know a Taylor series for the function 1 over 1 minus x, right? That's just the sum x to the n equals 0 to infinity. And so now, if I want a Taylor series for this, well, I could just substitute in minus 2x squared everywhere I see x. And I can do that on both sides. So that would give me minus 1, or so that would give me 1 over 1 minus, and then here I want to substitute in a minus 2x squared. And so that would be equal to the sum n equals 0 to infinity. Now, where I see x, I'm going to substitute in minus 2x squared, and that will be to the nth power. Okay. Now, of course, I can simplify this a bit. This is the sum n equals 0 to infinity of, I could rewrite this as minus 2 to the n times x to the 2n. Okay. But now what I have here is I now have a Taylor series for this function, 1 over 1 plus 2x squared, simply based on the fact that I knew the Taylor series for 1 over 1 minus x squared. Now, you may then wonder, well, what's the radius of convergence? Now, there are sort of two ways to think about this. One is you have a power series, try and determine its radius of convergence, okay? Now, this is actually a little tricky, though, because you don't have a power series that's like just to the nth term, okay? So to actually do this directly, you need to go all the way back to the ratio test, okay? So let's look at that. So again, this is a power series, but it's not really written in the usual form I'm used to because I have this x to the 2n power, whereas before I'm used to seeing this with like a x to the n power, okay? So if I wanted to know for what values of x does this series converge, I would go all the way back to the ratio test. And so I'd look at the limit as n goes to infinity of absolute value of a sub n plus 1 divided by absolute value of a sub n. Again, not using the coefficient type test for power series we've done before, because I don't have just an n here, I have a 2n here. Okay. So I could go all the way back here. My n plus first term would be a minus 2 to the n plus 1 x to the 2 times n plus 1 in absolute values divided by, then I get a minus 2 to the n x to the 2n. And sorry, let me not worry about the limit yet. Let me first just simplify this ratio. So let's see. In absolute values, this is going to become a 2 to the n plus 1, and then an x to the 2n plus 2 over 2 to the n times x to the 2n. Sorry, and the x's should be in absolute values. Right? The 2's I've taken the absolute values of. And so let's see, what do I end up with? I end up with a 2 that's left in the numerator. So all that'll cancel is 2 to the n will cancel in both. We're left with a 2 to the first here. And then here I'll be left with an absolute value of x to the 2 in the numerator. Now, what is this is sort of the ratio of the consecutive terms. Now I need to look at the limit as n goes to infinity of this ratio. But now notice that this ratio does not depend on n, right? This is a constant as far as n is concerned. And so this limit will just be this. And I know by the ratio test, I'll get convergence when this is less than 1. So when is this less than 1? Well, this is less than 1 when the absolute value of x squared is less than 1/2, which is when the absolute value of x is less than 1 over square root of 2, which is when x is between negative 1 over square root of 2 and 1 over square root of 2. Now, you can check endpoints here. You'll actually get that it converges for these x values. It doesn't converge at either endpoint. You can check those. It's just sort of an algebraic exercise to check those. But you get convergence on this interval from the ratio test. Okay. But now let's say you didn't want to go all the way back and you wanted to use the fact that you know that this is valid. Right, for x values between -1 and 1. Okay. Well, when you make the substitution, right? So you make a substitution, right? 1 over 1 minus, plug it in, minus 2x squared. Okay. That ended up giving us this series. Okay. And that's going to be valid. I could just make the substitution into the interval of convergence as well. So minus 2x squared 1. And sorry, that's cut off a bit over there. So minus 1 less than 2x squared. Okay. And so now here, right, I could do all the same things. So if I divide everything by -2, that's going to give me a minus 1 over root 2, or sorry, minus 1 over 2. And this is going to give me a 1 over root 2. And then if I square root everything, sorry, I wrote a root 2 up here already. It should be 2. I'm getting ahead of myself. Now, there is a slight sort of algebraic problem here that I have to deal with. And really the issue here is if I look at this quantity is always going to be negative. Okay. And so if I wanted to be actually really precise about this is always going to be negative. So it's never going to be like equal to 1. It's never going to get up here to 1. So really, if I want to be very precise about this, I should say, you know, this is always going to be negative. So it's always going to be less than 0. So let's see actually when that is satisfied. But again, what will actually happen here, you'll divide by -2. That's going to flip your inequalities because it's negative. and it's going to give you this. But when is x squared less than 1/2? Well, you have sort of this plus or minus issue, and that happens when this is true. So we can sort of rigorously justify this. Before I was just doing some sort of sloppy sleight of hand to get to the right answer. But again, I can also get to, my point being, I can also get to the interval of convergence by knowing the interval of convergence of the original series and then just substituting in my change of variables there as well. So again, two ways to sort of get at the same thing. Okay. Point being, I was able to create a Taylor series here by just plugging into a Taylor series that I already knew. Let's look at another example of this. So imagine you're asked to find a Taylor series for e to the x squared, centered at x is equal to 0, and to find its interval of convergence. Okay. So again, here we want to say, well, what's maybe a related Taylor series we know? We know that e to the x is, its Taylor series is a sum n is equal to 0 to infinity, x to the n over n factorial. And I know that that is true for all x values. Okay. So immediately I sort of know, well, no matter what I substitute in for x, this is still going to converge. Okay. So I sort of already know its interval of convergence is all real numbers. Its radius of convergence is infinite. Now I just really need to make the substitution. So I'm going to substitute in x squared everywhere I see x. So then e to the x squared will be the sum n equals 0 to infinity. Then for x, I'll substitute in x squared to the n over n factorial. And this is the sum n is equal to 0 to infinity. That would be x to the 2n divided by n factorial. Okay. And again, this will hold here for all x values, right? Because this series worked for any x value I plugged in. Now I'm just plugging in a different x value, in this case x squared. This series will still converge. Now, one really nice thing about this is that if you'll recall, we had a really difficult time. Like, this is a function whose integral you cannot express, or whose antiderivative you cannot express in terms of nice elementary functions. But now that you have a power series expression for it, you might actually be able to work with it a bit simpler, and we'll see how sort of that could work in a bit. And speaking of integration, we can also integrate power series. So imagine you were asked to find a Taylor series for the function h of x is equal to arctangent of x. Now again, you can start trying to write out derivatives of various orders, and I mean, you can go back to the definition. Or you could also recognize that this function h of x, which is arctangent or tangent inverse of x, this is really the antiderivative of 1 over 1 plus x squared dx. And this, well, I think I could probably write a Taylor series for this, right? Because I could recognize this is really 1 over 1 minus negative x squared. So to get a Taylor series, I'll first start with a Taylor series for this. There's a Taylor series there. Now I'm going to substitute in negative x squared. I'm going to sort of work my way back up. Substitute in negative x squared here. And let me do a bit of simplification. This is really minus 1 to the n times x to the 2n. Okay. And now, okay, that's that. Now I want to integrate this. Now, you should be a little sort of skeptical of what I'm about to do. What I'm going to do in a minute is I'm going to say, well, this is just a sum, and I can integrate a sum term by term by term. Okay. Now that's true for finite sums, but this is an infinite sum. And the conditions under which you're guaranteed to be able to do this are really a bit beyond what we would normally discuss in calculus 2. It's really more of a topic for discussion in a course in real analysis. So I'm going to just sort of suffice it to say for now that for the types of functions that we are working with, when the Taylor series converges, you can swap these. You can swap the sum and the integral. So what I'm going to do then is I'm going to think of this as the sum n equals 0 to infinity of, now I'm going to just integrate each of these terms. Now, if I do that, myself a little more room, work my way back up here. I'll get a sum n equals 0 to infinity. Now, I'm integrating with respect to x, so this minus 1 to the n, that's just a constant as far as that's concerned. The integral is concerned. I can just pull it out. And now I need to take an antiderivative of x to the 2n. So I'll increase the power by 1, x to the 2n plus 1, and I'll divide by the new power. And now what I have here is a Taylor series for arctangent of x. How did I get it? I took the Taylor series for 1 over 1 minus x, used it to help me find the Taylor series for 1 over 1 plus x squared, then integrated that term by term to get here. Okay. Now, I actually have to be a little careful about something, though, because if you remember, the antiderivative of this isn't necessarily arctangent. The antiderivative here is arctangent of x plus some constant. So, sorry, collapse. Come this way. Right? The antiderivative of this is arctangent of x plus some constant. So it's possible that this differs from arctangent by some constant. And so what the only thing we need to check is we need to check and make sure we have at least one function value correct to make sure this isn't shifted. So if I plug in 0, arctan of 0, right? So, right? So that's like asking if that's equal to L, that's really asking where is tangent of L equal to 0. Well, tangent is sine over cosine. This is just at 0, right? It's when sine of L is 0. So that's 0. Now notice if I plug in 0 here, what am I going to get? I'm going to get a sum of a bunch of zeros. It's just 0. So in fact, this does match up. The C here that you get is just 0. So in fact, this is equal to that Taylor series. Okay. Again, point being, we can use integration, right? We can take a Taylor series. In this case, we found a Taylor series for 1 over 1 plus x squared. We use that Taylor series to then find the Taylor series for its antiderivative, arctangent of x. Okay, we can do it with integration. Why not differentiation, right? So imagine I wanted to find a Taylor series for the function 2x e to the x squared. Well, notice that this function 2x e to the x squared, this is really just the derivative of e to the x squared. right? And I know a Taylor series for e to the x squared, right? We just found one not very long ago, right? So this would be the sum n equals 0 to infinity of, so x to the 2n over n factorial. So that's my e to the x squared, and I need to take a derivative. Now again, in general, you might say I've got a sum, I can take the derivative term by term, and certainly that is true for finite sums, but we have infinite sums. Again, in an analysis course, you might talk about under what conditions can I take this derivative of this infinite sum term by term and expect it to actually converge to the derivative of the function. But again, suffice it to say that for the types of functions we're going to be dealing with, when this Taylor series converges, then everything is fine. So we can actually just differentiate this term by term. So this will be the sum n equals 0 to infinity of, now just take a derivative of each term. Now again, you're taking a derivative with respect to x. So the n things are really, they're just like constants essentially. I have to be a little bit careful here. If I think about the very first term, the n is equal to 0 term, that term is going to be x to the 0 over 0 factorial. It's just going to be 1. And its derivative is 0, so it disappears. So this new sum starts at n is equal to 1, because the derivative of the 0th term over here was just 0. Okay. Now, for all the rest of the terms, I'm going to differentiate these like normal. So the 2n is going to come down. X to the 2n minus 1, still divided by n factorial. And I can clean this up a bit. This is the sum n equals 1 to infinity. The n and the n factorial, that can actually become, so this will be x to the 2n minus 1. There'll be a times 2 there, over n minus 1 factorial. So the n here is going to cancel with the first n in that n factorial. You'll be left with n minus 1 factorial. Okay. And if we really wanted to, we could re-index and sort of shift this series to start at 0. There's no reason right now to want to do that. Here's a perfectly good series for the function 2x e to the x squared. Again, how did we get it? We started with a series for e to the x, used that to construct a series for e to the x squared, and then took the derivative of that to get the series for to get the Taylor series for 2x e to the x squared. Okay. So again, integration and differentiation term by term of Taylor series can be a very powerful way of generating new Taylor series. Now, there's actually another way to do this. Instead of thinking of this as sort of the derivative of e to the x squared, I could think of this function also as just 2x times e to the x squared. So I could also think of this as 2x times e to the x squared, in which case I would get 2x times, now this sum for e to the x squared is x to the 2n divided by n factorial. Now, I could just distribute this xn and distribute the 2n. So let's see, x times x to the 2n, that would give me an x to the 2n plus 1. And then I get a 2 that got distributed in divided by n factorial. Now, you might be looking at this and going, but wait, that's not what we got before, right? The answer we had previously was the sum n equals 1 to infinity, 2x to the 2n minus 1 divided by n minus 1 factorial. Okay. Now, again, if you start writing out terms, you'll see that these are actually the same. And one way to get at that is by re-indexing to really see that these are the same. So imagine I set k equal to n minus 1. Okay. Now, when I first start to do this, okay, when n is 1, k would be 0. So this would be a sum k is equal to 0 to infinity. I would get, let's see, down here I would just get a k factorial. That's pretty easy to see. Now up here, this is a little bit trickier, but let's take a look at this. I want to express 2n minus 1. So if I were to take this and double it, I'd get 2k is equal to 2n minus 2. And then, let's see, I want 2n minus 1, so let me add 1 to both sides. So 2k plus 1. So this would give me that 2k plus 1 is equal to 2n minus 1. So this 2n minus 1 would become 2k plus 1. We get x to the 2k plus 1. And now you can see, right, if you can switch all the k's back to n's if you want, right? This is just sort of a dummy variable as we go index through our terms, right? These are really the same series, right? So again, these are, in this case, we have two different methods for arriving at a Taylor series for the same function. One thinking about it as a derivative of another function, one thinking of it as sort of a power of x times another function. Okay. Now, in this case, it was sort of very clearly we're multiplying by some power of x. But let me also point out that you can do this when it really looks like you're dividing by x as well. So imagine you're asked to find a Taylor series for 1 minus cosine of x divided by x. So if we take this piece by piece, the first thing we notice is maybe that cosine, and we think, oh, okay, great. I know a Taylor series for cosine. So the Taylor series for cosine of x is the sum n equals 0 to infinity, minus 1 to the n, x to the 2n divided by 2n factorial. Great. Okay. But now I need 1 minus cosine of x. Okay. Now getting minus cosine of x, that's actually not too bad, right? I could just put a minus there, and then I would negate everything here. That's like multiplying every term by -1. So I could just change that to a n plus 1. Okay. But now I need to add 1. Well, let's see. If I add 1 over here, let me think about the following. I'm going to take this sum. So I'm going to add 1 to this sum. But if I think about when n is equal to 0 here, what do I get? When n is equal to 0, I get -1 x to the 0 over 0 factorial. So I get -1 times 1 over 1. I get -1. So the first term here is -1. If I add 1 to that, I'm going to get 0. And then I'm just going to be left with all the rest of the terms, right? So I'm sort of breaking off the 0th term, which is -1. I'm adding the 1 to that, those add to 0, and then I'm just left with this. Okay. Now, the last thing I want to do, I want to sort of divide by this x. I can really think of this as multiplying by x to the -1. So if I multiply everywhere by x to the -1, I can then distribute that through. And that's just going to decrease my power of x by 1. And so I end up with a Taylor series, right, for this function 1 minus cosine of x divided by x by just manipulating through my Taylor series for cosine of x. First I negate it, then I add 1 to it, then I multiply by x to the -1 to end up with this Taylor series that we see here. Again, if you wanted to reindex this to start at 0, you certainly could. Generally speaking, it's not necessarily a big deal either way. The only times it's nice is when you have two series, one of which starts at 0 and one of which starts at 1. It may be hard to tell whether or not they're the same series, just shifted. So often we'll shift one of them to start at the same place as the other so that we can really tell whether the series are the same or not. Now, I want to conclude this video. I mean, this video has really been sort of showing you a collection of tricks which can be helpful in finding some Taylor series. And I want to conclude this with sort of one more extended example. And again, it will help tie together sort of a lot of the series stuff we've been working on. So imagine you were just given this series, right? You could go and do a convergence test. I think ratio test will tell you pretty quickly that this series converges. It's positive terms, so it converges absolutely. But of course, none of the series tests are going to tell you what it converges to. But it actually turns out that this series converges to the value 1. And we actually want to show that, that this converges to 1. Okay. Now, in order to do that, we're going to have to sort of do this in a couple different ways. So the first thing I'm going to do is I am going to find a Taylor series for this function. Okay, now that's a very strange looking function. And then I'm going to evaluate it at 1. Okay, now notice that if I evaluate this expression at 1, I'm going to get e to the 1 minus e to the 1 plus 1. So it's going to be 1 over 1. I'm going to get 1. Okay. So what I'm going to see is that if I evaluate this at 1, and if I evaluate the Taylor series at 1, this gives me, this is what I get more or less for the Taylor series evaluated at 1. It has to converge to this function evaluated at 1, and this function evaluated at 1 is 1. Okay, so let's sort of take a walk through this step by step. We're going to start by finding a Taylor series for this function x e to the x minus e to the x plus 1 divided by x squared. Okay, so I want, again, the Taylor series for x e to the x minus e to the x plus 1 divided by x squared. Now, you could think, well, I'm just going to start with the Taylor series for e to the x. I'll multiply by x and sort of do a bunch of stuff that way. It actually turns out that you'll run into some difficulty combining terms there pretty quickly. It's not impossible, but it's just a little tricky. What I might want to actually recognize is that this is the derivative of e to the x minus 1 divided by x. Okay, so if I look at this, if I were to take a derivative of this, it would be what? Bottom times the derivative of the top. Derivative of the top is just e to the x. So it'd be x e to the x minus top times the derivative of the bottom. So minus the top. Well, minus e to the x minus negative 1, give me a plus 1, and then divided by the bottom squared, right? So the derivative of this is, in fact, this. Now I want to find a Taylor series for this, okay? So let's see, I've got, let's start with e to the x. So sum n equals 0 to infinity of x to the n over n factorial. Now, let's see, I'm going to want to subtract 1, but notice that the 0th term of this series is just 1. So I'm really just dropping off the 0th term. And now I need to multiply through by x to the negative 1. So that's just going to decrease all my powers of x by 1. All right, I get that. All right, now this is the thing that I now want to take the derivative of. Okay, so let's see, if I plug this in over here, then I want to take, I'm going to take the derivative term by term. But this, when n is 1, what do I get? I get x to the 0, which is 1 over 1. So the n is equal to 1 term is just 1. When I take a derivative, it's going to go away. Now, all the rest of them I can compute by power rule. Okay, so what does power rule tell me? N minus 1 comes down, x to the decrease the power by 1 all over, still n factorial. Okay. And again, that's for all the terms from 2 up to infinity. Okay. So now I have, right now, that x e to the x minus e to the x plus 1 over x squared is equal to this. Now, I should be a little careful. I should wonder what the radius of convergence is. It turns out the radius of convergence here is infinite. So this does converge for every value of x, and for every value of x, this series converges to this. So now what I'm going to do is I'm going to take both sides of this, and I'm going to evaluate at x is equal to 1. So over here, as we already discussed, if I evaluate this at x is equal to 1, I'm going to get 1. If I evaluate this at x is equal to 1, I'll get the sum n is equal to 2 to infinity of n minus 1 times 1 to the, well, 1 to the any power is just 1 over n factorial. Now, if you go back a slide, and this will overlay a little bit, but just to quickly see, right? This is almost what I want, right? But not quite. So what I really want, right, is I really want to see the sum k over k plus 1 factorial, k going from 1 to infinity. So let me just try a shift here, okay? And so, in fact, if I take this series and re-index it, so I set k equal to n minus 1, so I'm just going to shift my n's down 1. Then when n is 2, k will be 1. This n minus 1 will just become k, and this n, right, if I solve this for n is k plus 1, so this n will become k plus 1 factorial. So this series is actually just equal to this, right? It's just a re-index sum. But this is, sorry, but this series is equal to 1. So this series, the re-indexed version, also is just equal to 1. Okay. So in this last example, we see how to take all of these different sorts of rules and tie them together, in this case, to actually help us find the precise value to which a series converges. Again, you can prove this series converges using ratio tests, but to determine what value it actually converges to, you actually need to use these sorts of methods. There are other methods for determining values to which series converge. There are sort of some combinatorial methods, things that deal with sort of like counting type problems. You can sometimes use things from like statistics or probability theory to help you with these sorts of things. But in this case, using the tools that we have from Taylor series can be very helpful in determining these. So with that, we actually conclude our discussion of Taylor series and conclude our discussion of material for this course. So you'll have a chance to practice working with some Taylor series based on this material, and then it'll be time to review for the final exam. As always, if you have questions, please do feel free to reach out and let me know how I can help you.